everybody. Today, instead of being in front of the whiteboard like I typically will be, I'm actually shooting from behind my iPad because I have this little gremlin of a cat that loves to crawl all over me when I'm trying to do things and likes to stand in front of the board as seen in previous iterations of my YouTube videos and YouTube content. So with that in mind, and if you can even hear her purring, I'm going to try and talk a little bit about Joule's free expansion experiment. Now, Mr. Joule was a scientist. He lived in the mid-1800s, and he is most well known for giving us things like the first law of thermodynamics, things like Joule heating, and even disproving something like caloric theory, which stated that heat was actually made out of this weird fluid that flowed from hot to cold areas, because we needed to explain it somehow. That was the best that we had. But more importantly today, in relation to what we've been studying in this section of thermodynamics, is that he had this pretty neat little experiment that actually showed the mathematical proof that we worked on last time pertaining to how energy for an ideal gas can be considered independent of the volume that it occupies. So what Joule did for his experiment is that he got a container and he added a partition to this container. He filled it with a gas that was sufficiently dilute that it would be considered an ideal gas, and he put a little valve in that partition that separated the gas from the vacuum on the other side of the container. Now he put this container into a bath of water as to isothermally isolate that system. Now incrementally what he would do is that he would open the valve just a smidge to induce a quasi-static process, right? So the gas could flow freely from one side of the container to the other, but it happened slowly. And as a consequence of this, no work was actually done by the gas on the container as it was filling the other side with, air. So as a consequence of this no work being done, we realized that the change in energy itself can be equal to the change in heat that is exchanged in whatever's going on in this particular interaction, right? So more specifically, the delta E would measure a change in energy for the gas itself, right? Now, an important detail that I have so conveniently left out is that hooked up to this container was a thermometer. This thermometer was not hooked up to the box itself, but rather the water bath, and it would take some sort of measurement trying to get a change in temperature of the water, right? Now, in doing his experiment, what he noticed is that there wasn't really any sort of major change in the temperature of the water. With his instrumentation at the time, what it showed, it was basically zero. So, even though you've had some sort of gas going into this other vacuum doing some sort of supposed change in heat, possibly speaking, or rather the energy, if there is any sort of change in energy, could be described by this change in heat, there was no change in the temperature. And because he did not register any sort of change in the temperature in the water, he can conclude that there was absolutely no gas, that no heat was transferred from the expanding gas to the water bath around it. So if our temperature of the gas remains unchanged while the gas changes its volume, we can write the function of energy of E of T and V as a difference, right? So the energy at our final volume minus the energy of our initial volume is equal to 0, and thus our initial volume energy is equal to our final volume energy, and consequently, if we take our handy-dandy little, oh my goodness gracious, my cat is doing biscuits on my legs right now. It's not very fun because she has little claws and it hurts. Consequently, our energy is completely and wholly independent of any sort of change in volume because our energy will be the same at the beginning volume as it is at the final volume, thus leading to that conclusion that we made at the end of last video, where the partial derivative of our energy with respect to volume holding temperature constant is in fact 0.